Hello, I'm Ratul Thakur from Engineering Physics Third Year, and in this video I'll be demonstrating an assembly language program that calculates the sum of an arithmetic progression up to first n terms. So I'll start with a basic terminology which is associated with arithmetic progressions. If we use a sub n to denote the nth term of the progression, the common difference can be written like this. The common difference is the difference between the consecutive terms of the progression, and we can define s sub n as like this, which is the sum of the first n terms of the arithmetic progression. So we need to implement a program that calculates this sum of first n terms Sn based on these parameters which are given to the program. The parameters which are given are the first term of the progression, which is a1, the common difference d, and the number of terms that are to be summed, which is n. So based on these three parameters, we need to write a program which calculates Sn, and the final result will be stored as a 16-bit number in the memory. So now let's get to the code. This is the first segment of the code, which just loads the data from the memory. So I'm assuming that the value of a1 is stored in the memory location 2000h, the value of d is stored in memory location 2001h, and the value of n is stored in the memory location 2002h. So this block of code loads the data stored in the memory location 2000 into b, and similarly this block loads the data stored in 2001 into the register d, and this loads the data stored in memory location 2002 into the register e. So the register b now has value of a1, register d has the value of d, which is the common difference, register e has the value of n, which is the number of terms which are to be summed. We also need to initialize the other registers. We need to set the C register to 0 because we will use this register to count the number of carries that are accumulated throughout the execution of the program, and we'll set the value of h equal to a1 which is now already stored in b, and this a1 is also evidently equal to s1, which is sum of just the first term of the arithmetic progression. So actually h will be used to store sum up to ith term in every iteration. This will be more clear in the next segment of the code. So this segment of the code is the main part of the program where the addition actually takes place. So the first thing we do is we decrease the register e. E actually stores the value of n. So if, for example, the value of n is 5, then this loop needs to run 4 times to perform the sum. So that's why we decrement e by 1 before we start the loop. As soon as the loop starts, the first thing that happens is the value of ai. Now I'm assuming that the register b during the ith iteration holds the value of ai, and this is true for the first iteration because in the first iteration register b holds a1. So in the ith iteration b should hold ai. Will implement the program in such a way that this is true. So ai is now loaded into the register a, and we now add d into the value which is stored in the register a, which is stored in the accumulator. So adding d stores the common difference, so ai is added with the common difference, which actually gives ai plus 1, which is the I plus 1th term of the arithmetic progression, and now this value is stored in the accumulator. And now we'll move this value back into the register b. So now register b holds ai plus 1, which is the I plus 1th term of the arithmetic progression. And we'll also assume that the register h stores the value of si, which is sum up to I terms. So this is for the ith iteration, and for the first iteration, like when the loop runs for the first time, h should hold the value s1, which is indeed true because we set its value equal to a1, which is evidently equal to s1. So we'll move the value of si from h into a, and we'll add into that the value of ai plus 1. So ai plus 1 is added with the accumulator, which stores si. So ai plus 1 added with si gives si plus 1, which is sum up to the which is sum up to the I plus 1th term of the arithmetic progression. So this is actually the main result that we're looking for. But if a carry is generated, we need to take care of that. So if there is no carry, then we'll directly jump to this label, but if there is a carry, then we'll increment the C register, which will accumulate all the carries which are accumulated throughout the program. And after the carry has been taken care of, this value of Si plus 1, which is in the accumulator, is moved into the register H. And finally we decrement the register E, which stores N. So this is kind of a counter variable for the loop, so this controls how many times the loop runs. So now in the start of the ith iteration, the register B holds the value AI and the register H holds the value Si, and at the end of the ith iteration, register B will hold the value AI plus 1 and register H will hold the value Si plus 1. So after this loop has been completed, when this J and Z jump non-zero condition is when E is actually non-zero, this loop jumps to this label, like it keeps looping until E becomes 0, and when E becomes 0, this loop breaks. So when this loop breaks, all the addition which is supposed to take place has taken place, and the result will be stored in H, which is Si plus 1, and the carries will be accumulated in C. The result which is stored in H, which is Si plus 1, is also stored in A. So Si plus 1 is actually stored in both H and A. And after the loop has done executing a sufficient number of times, the final result in H and A is Sn, and the carry obviously is in the register C. So after we have obtained the results, we need to store them in the memory, and we'll store the value which is in A, which is Sn. We'll store that value in the memory location 2003, which is the lower nibble of our result, and then we'll move the value stored in C, which is the carry, into A, and we'll store that value in the next memory location, which is 2004. This is the higher nibble of our result. So the final 16-bit result comprises of these two things, like the lower nibble and the higher nibble. And let's see an example of this of execution of this program to understand this better. So this is the status of the memory before the execution of the program. This is the data. This is 10 is A1, 12 is the common difference, and 10 is number of terms which are to be summed. And after execution, the memory location 2003 and 2004 have the values 128 and 2. So this is decimal. These are decimal values. So I'll convert these this lower nibble and higher nibble into hexadecimal form, and then I'll put these together to form a 16-bit number. This is the higher nibble, and 80, which is the lower nibble, and I'll convert this to decimal, which gives 640 as the result. So the sum of the arithmetic progression with these parameters results in this 640 decimal result. This is what our program gives us. Now we can verify this using the mathematical formula which is available for the sum of n terms of an arithmetic progression, which is this. We substitute these values of the parameters into their places, and this also gives us 640 as a result. So this verifies that the output that our program gives is indeed true, and our program is working correctly. So that was it. I hope this was helpful. So yeah, thank you.